All right, I'm gonna get started. The camera is scrolling. All right, good afternoon. Welcome back to Math and Modeling Methods. We're up to lecture 6. Yep. All right. So far we've covered vector field theory and its differential operators, integral identities, and we've put into practice. And today we're just going to also talk about specific application and implementation of the Stokes Theorem. We looked at the Gauss diversity theorem and how that can be turned into other forms, and how do we go about verifying. Well, it doesn't need to be verified. It's an analytical exact expression. So just for the matters of validation, we try to confirm it for certain cases. So in the case of the Stokes theorem, we did an example of solving the left-hand side and the right-hand side of the Stokes theorem. But today we are going to look at a specific consequence of what happens when we have a vector field that is irrotational, and what does it imply? So this is the general form of the Stokes theorem that we're used to, where we can actually transform a surface integral, not a closed surface integral, so the integral over a surface, we can pass it to the line that wraps that surface in that particular form. Okay, so that means that we can reduce the dimensionality of the integral from 2D integral to a 1D integral, and obtain the same result. Now let's assume that for this particular case, F is a force field. Okay? And also assume that F is irrotational. Assume that F is irrotational. We've looked into the physical implications of these when the vector field is a velocity field in fluid mechanics. When that vector field is v, and v is the velocity field of a fluid flow, we looked at the implications of when the flow field is irrotational. That means that the flow particles do not rotate about their own axis along a flow path. Basically, that's what it means for a flow field to be irrotational. In this case, we're going to see what are the implications of a force field being irrotational. And the physical implications of that can be derived directly from the Stokes theorem. So, if we have a force field that happens to be irrotational, whatever that force field is, by the way, it can be a magnetic field, it can be an electric field, anything that exerts a force over anything else, okay, it can be a gravitational field, and it happens to be irrotational, then if we look at the Stokes theorem, we find that the left-hand side integral is 0, and therefore the conclusion is that f dot dr is equal to 0. That is a consequence. All right, so that means that if I take the integral of that force field along a line that is closed, any line that is closed, I'm going to get 0. So this means physically that the total work, well, why work? Because work is equal to force times distance, and that's basically what we're doing with that integral. It's force times dr. Is basically we're integrating force along a line, multiplying them. So we're essentially getting the mechanical work exerted by the force field. But if we do so in a closed path, then this is 0. As long as the force field is irrotational. So that is what it means for force field to be irrotational. And that's why we also call irrotational vector fields are also called conservative fields. And that's for that reason. Because energy is conserved. There's no work being done to go from point A back to point A on whatever closed path. Now, if you think about it, you have a particle that lives in a force field. Let's say that the force field is gravity, and then you want to move that particle in any direction in whatever trajectory and bring it back to its own location. The amount of work that needs to be performed to do that is 0. That also implies that going from point A to point B is path independent. If you think about it, that implies directly that the work is path independent. Okay? We're going to prove it mathematically, but if you think about it, going from point A back to point A gives you 0. That means that going from point A to point B in one trajectory or in another trajectory should yield exactly the same amount of work. Okay? So, these also implies that the work from any point A to any point B is path independent. As long as the force field is conservative, which is another word again for irrotational. Okay, so let's see. Let's try to prove these. Well, you can, from the fact that if the closed path integral is 0, you can conclude that any work therefore will be path independent. But we can prove this. Prove that the integral from A to B of f dr is path independent as long as f is conservative or irrotational. Okay? So let's see. Now, if the curl of f is equal to 0, then that means that f can be formulated in terms of the gradient of a potential function. And that is, again, because the identity that says that the curl of the gradient of any function is equal to 0. Okay, we've done this before. We've done this for the velocity potential. Now this is a force potential. So in this case, is a force potential. Now force potential is nothing but energy. Okay, we'll see how that comes about. All right. So recall that F is equal to Fx in the x direction plus Fy in the y direction plus Fz in the z direction. Okay, each of those components, Fx, Fy, and Fc, are functions of space. Could be functions of space. And then we have dr being equal to dx in the x direction plus dy in the y direction plus dz in the z direction. All right. Therefore, f dotted into dr comes up to be fx dx plus fy dy plus fc dz. But the force field is equal to the gradient of a force potential, and therefore that means that the x component of the force field is d phi dx, the y component of the force field is d phi dy, and the z component of the force field is d phi dz. All right? And therefore, f dotted into dr can be reduced to d phi dx plus d phi dy plus d phi dz. I'm sorry, phi dy, and d phi dz. All right. So what does this mean? F dot dr is equivalent to saying d phi dx dx, d phi dy dy, d phi dz dz, where phi is the potential that generates that vector field. Okay, and we know that there's such a potential because the vector field happens to be irrotational. If the vector field weren't irrotational, then the potential doesn't exist. All right, so do you remember chain rule? From chain rule, given a function phi of x, y, and z, what is the differential of phi? The total differential of phi. It will be the partial of phi with respect to x times dx plus the partial of phi with respect to y times dy plus the partial of phi with respect to c times dz. That's identical to what we have up there. Right? And therefore, f dotted into dr is simply d phi. And therefore, the integral from a to b, any point A to any point B, regardless of how we get there, of that force field vector dotted into the r is equivalent to the integral from a to b of d phi. And what is the integral of d phi? It's just simply phi evaluated at a and b, which is equal to phi b minus phi a. And this is definitely path independent. Mm-hmm.
It should be DZ.
Oh yeah. Sorry. It's easy. All right, so that's a mathematical proof of that. We could have proved it by inspection, knowing that the integral over closed contour 0 implies automatically that that integral is path independent. But this is the official proof. Okay, so if the force field is irrotational, then there is such a thing as a potential. It only exists because the force field is irrotational, and therefore the work performed between 2 points A and B, regardless of the path that the particle takes to go from A to B, will be equal to the potential evaluated at B minus the potential evaluated at A. Okay? So for example, in a gravitational field, the force field is basically the acceleration of gravity in the z direction, right? That's it. It's a force field, the acceleration of gravity in the z direction, times the mass. And the potential of gravitational potential is just the potential energy. The potential energy, which is mass, gravity, times elevation. So regardless of whether you go from one elevation to the next on a straight path or on a curved path, the amount of work performed on that trajectory, on that motion from A to B, will be simply the potential energy evaluated at B minus the potential energy evaluated at A. That's it. So is that clear? And that's a consequence of the Stokes Theorem. So, example. Let's look at that example in particular. Gravitational force field. So we have the force field 0 in the x direction, 0 in the y direction, minus mass times gravity in the z direction. So we have a localized gravitational field. Great, that's assuming localized on the surface of Earth. It's just the gravitational acceleration on Earth. In space it will be a little different, plus it will be in spherical coordinates, obviously. If we take, well, it is obvious because all of these is a constant, that if we take the curl of this field, which is equal to dx, or the determinant of this particular matrix, d dx, d dy, d dz, 0, 0, minus mg. We don't really need to prove that this is equal to 0, right? So we're taking derivatives of either 0 or constant in all directions. So it's the determinant of that matrix, which you can do by augmenting to the right or augmenting to the bottom. So that means that F is conservative. Okay, and therefore, the work done on this field is path independent. Moving from one elevation to the next, or from one point to the next, really doesn't matter what path you take. All right, so let's look at what the gravitational potential is. That would require us to derive that function phi, that gravitational potential. So, whose phi? Such that F is the grad of phi. Therefore, F, which has three components, 0, 0, and 0, should be equal to the phi dx, the phi dy, and the phi dz. I'm sorry, this will be minus mg. third component of that force field. So that would mean that this is the phi, dx in the x direction, plus the phi, dy in the y direction, plus the phi, dz in the z direction. So somehow we have to integrate phi from these three equations. Right? So we have d phi dx is equal to 0, and therefore phi should be equal to the integral of 0 dx. What is the integral of 0? Constant, right? Should be a constant. But it can also be a constant, it can also be a function of y, because this is a partial derivative, so any function of y, when we differentiate, we get 0. So this can be, let's say, a constant 1. It can also be a function 1 of y. It can also be a function g1 of z. Or it can also be a function h of y and z. Any of those options will be true for that equation. Right? Because if I take any of those functions for phi, for any of those options, and differentiate it with respect to x, I'll get 0. Is that clear? If phi dy is equal to 0, then implies that the integral of 0 with respect to y can either be a constant 2 plus a function 2 of x plus a function g2 of z plus a function h2 of x and z. So any function of x, any function of z, any combination of x and z, or any constant will yield a derivative that's equal to 0. And the third equation tells me this is minus mg, therefore phi is equal to the integral of minus mg dz and this is minus mgz plus a constant 3 plus any function 3 of x plus any function 3 of y plus any function 3 of xy. All right? So now I have to match all these three results, because all three results should yield what phi is. All right? So basically, any function of c would appear in the last integration. So this one and this one appear right here. Any function of x, y, and z should appear commonly on all three results. A combined function of x, y, and z would appear commonly in all three results for any of these cases where you're trying to find a potential given a vector field. Okay? Any function of c will appear on the z integration. Any function of x will appear on the x integration, there's none. Any function of y will appear on the y integration, there's none. Any function of y and z will appear in combination together of these two integrals, and there's none. So basically, these two functions are this one right here. This function of y should actually show up here, and there's none. This function of y should show up here, and there's none. this function of x should show up here, and there's none. This function of, and so on and so forth. So at the end, the conclusion is that phi of x, y, and z, the only thing that appears is minus g mgc, and there can be a constant, but the constant actually doesn't do anything. So I'm going to write here plus a constant, but that really doesn't do anything. And then you can verify that this is the case. The gradient of this function is 0 in the x direction, 0 in the y direction, and minus mg in the z direction. And that's it. So that's the actual answer. And this is the gravitational potential energy. The work would be equal to the integral from A to B of force dotted into the R, which is equal to the integral from A to B of the phi, which is equal to phi evaluated at point B minus phi evaluated at point A. And therefore, the work is equal to minus mg times cb minus ca. All right. Any questions? This is a simple example, especially when it comes to finding the potential, because those integrals are pretty straightforward. Let's look at another example. If F, this force field, is now x squared Ex plus xy Ey. Okay, this is a force field on the plane, x and y. And it can be due to anything. It can be an electric potential field or a force field or whatever it means. That produces a force vector at any location given by that representation. Now, if we take the curl of F, which is again Ex, Ey, Ez, Edx, Edy, Edz, x squared, xy, and 0. Right? So the vector field, or the curl of the vector field, will be in the x direction we have d0 dy, and in the x direction coming back we have minus d dz of xy. Yes. In the y direction, we have d dz of x squared minus, coming back, we have d dx of 0. And in the z direction, we have d dx of xy minus d dy of x squared. So what is the curl of this vector? In the x direction, 0 and 0. In the y direction, 0 and 0. And in the z direction, the derivative with respect to x of xy will be y, and the derivative with respect to y of x squared will be 0. So it just simply be y in the z direction. So f is not conservative. I guess we can say it's liberal. Not necessarily. So, okay, this means that somehow, because the curl is not 0, it implies that not only we're going to find that the work is not path independent, it's path dependent, but also it would imply that the scalar potential function doesn't exist. Okay? Because of that identity, that can be a cause or a consequence. Since the curl is not 0, then the potential doesn't exist. You cannot find it. We can try, but we will not find it. So, because this is not 0, then f is not equal to the gradient of phi. That means that phi does not exist. What's going to happen is that if you try to find phi, if you try to find a phi such that f is equal to the grad of phi, you're going to find an incompatibility between the two integrals that you're trying to take. Okay, we can try that. So, if we try to find phi such that the grad of phi is equal to f, then this is what we're going to get. Okay, so what is f? It's right here. So we're going to say if the grad of phi is equal to f, then the phi dx is going to be equal to x squared, while the phi dy is going to be equal to xy. Right? This is the gradient of phi and should be matching f. That means that phi should be equal to the integral of x squared with respect to x. And what is that? That would be x cubed over 3, right? Plus any function f that is a function of y would come in here as a constant, plus any constant c1. The second integral implies that phi should be equal to the integral of xy with respect to y. What is that? That would be xy squared over 2, right? Plus any function g of x plus constant c2. All right? So, the function of x, standalone function of x, should be found on this integral, and there it is. That's x cubed over 3. And a standalone function of y should be found on this integral, and there it is 0. And any combined function of x and y should be common on the two integrals. There's a combined function of x and y, it's xy squared over 2. That should have appeared on the first one. Alright? So if we attempt to say, if we say phi is equal to xy squared over 2 plus x cubed over 3, for instance, these functions right here should have appeared here. The common function of x and y should appear on both integrals, and there's none on the first one. So if we even attempt to do this, and we take the gradient of phi, what is the gradient of this function right here? The derivative of these with respect to x is? That would be y squared over 2 plus x squared, right? In the x direction. And in the y direction, we have xy in the y direction, right? That's the gradient. Is that equal to f? No. Which is not equal to f. So that phi is incorrect. Actually, phi doesn't exist. You can try over and over and over, and you will not find a phi whose gradient gives you this. The only way that's possible is if f is rotational. All right. Is that clear? Okay. So now let's do an exercise here of determining whether the work is truly path dependent. And let's say that we're on the plane xy, and point A is 0, 0, and let's say point B is 1, 1. Okay, and we want to take, and the force field is traversing that plane, and we want to go from A to B on a straight line, like that. This we're going to call path 1, such that y is equal to x. That's the line y equal x. And another choice would be to take another path. For example, if I want to go like this, path 2, y equals x squared. Okay? Both will take you from point 0, 0 to point 1, 1. And another choice would have been, okay, go from here to here, and then from here to here. Okay, take 2 paths to get to point B. You can try that later. All right. So let's take path 1. Y is equal to x. So we are going to be doing the integral from A to B of f dotted into dr, which is equal to the integral from A to B of f is equal to x squared dx, that's what dr is, and fy is equal to xy dy. So we're going to be looking at that integral, and that would be the integral from A to B of x squared dx plus the integral from A to B of xy dy. And on path 1, y is equal to x. So path 1, y is equal to x. That means that dy dx is equal to 1. That means that dy is equal to dx. Right? So basically the integral between a and b of f dr through path 1 I'm going to call it work through path 1 is equal to the integral between 0 and 1, that's the value of x equals 0 to the value of x equals 1 of x squared dx, plus the integral from 0 to 1, that's the value of x equals 0 to x equals 1 of x dx. Right, so we've replaced this y right here with x, and we've replaced dy by dx. The limits of integration on x are from 0 to 1. So this is equal to the integral from 0 to 1 of twice x squared dx. So the work through path 1 will be equal to 2 x cubed over 3 between 0 and 1, and therefore the work through path 1 is equal to 2/3. Whatever units those are. It ends up being force times distance, but whatever units of force and whatever units of distance. All right. That's path 1. Path 2 means that y is equal to x squared. That curve also passes through points 0, 0 and 1, 1. When x is equal to 1, y is also equal to 1. When x is equal to 0, y is equal to 0. dy dx is equal to 2x, and therefore dy is equal to 2x dx. That's a transformation from one differential to the next. So the work along path 2, which will be the integral from a to b of f dot dr, will be the integral from 0 to 1 of x squared dx plus the integral from 0 to 1 of x times x squared times 2x dx. So the work through path 2 is equal to the integral from 0 to 1 of 2x to the 4th plus x squared dx. That would be twice x to the 5 divided by 5 plus x cubed divided by 3, evaluated between 0 and 1, and that would be 2/5 plus 1/3, and therefore the work along path 2 will be whatever that is. It's 15, 6 times, that's 11, 15. So the work along path 1 is different to the work along path 2 because f is not conservative. You can try any other path. You can try y equal to x cubed, which also passes through those points. You can try a multi-step path, horizontal and vertical, and then you can break these integrals up in two, and you still find 0, or find that the works don't match. Okay. Are there any questions? So, let me move along, and I'm going to talk about the last applications of vector field theory. More than an application, it's just the formulation of governing equations, which we'll later in the semester, towards the third part of the semester, we'll look at and try to solve. So, look at the applications to electromagnetism. We'll do a lot of applications in heat transfer and fluid flow, solid mechanics, but we'll be also solving wave equations. Okay? And I'm going to show you where those wave equations come from, why they end up being wave equations, why do they behave the way they behave. So, assume that we have a magnetic field H, and assume also that we have a perpendicular okay, and that this is an electric field, E. Okay, so it's that E electric field, and H is a magnetic field. S equal to the electric field cross the magnetic field is called the Poynting vector. Okay? And then we start with Maxwell's equations. Maxwell's equations. Maxwell's equations state that the electric field under some conditions is solenoidal. That means its divergency is equal to 0. It also states that the magnetic field is solenoidal under some conditions. It states that the curl of the electric field is not 0, but is equal to minus mu 0 times dH dt, and the curl of the magnetic field is equal to epsilon 0 dE dt plus sigma times E. Okay, I'm going to tell you what all these is. Well, under the assumptions that there's no polarization, no magnetism, and no charges. Mu 0 being the magnetic permeability. epsilon 0 is the electric permeability. And sigma is the resistivity of the medium. All right. So, again, what I'm going to do here is I'm not going to apply Stokes Theorem or Gauss divergence theorem. I'm just going to use these Maxwell's equations and a couple of identities to end up with the equations of electromagnetism, which are equations that we later on in the semester will attempt to solve. But in order to get to those equations, field theory or vector field theory is necessary. So I'm going to take the last equation there, fourth equation, and I'm going to take the curl of that equation. So if I take the curl of H, that would be equal to epsilon 0 times d dt times the curl of E plus sigma times the curl of E. And we're going to try to use, the identity that says that the curl of a vector field A is equal to the gradient of the divergency of A minus the Laplace of A. That's a vector identity, which I think I asked you to prove in homework. I think. I don't remember correctly. If I remember correctly. So you just basically try to show that the left-hand side for any vector ax, ay, az is equivalent to what you find on the right-hand side for a vector ax, ay, az. All right. So if that's the case, I'm going to use it up here, and that will yield the gradient of the divergency of the magnetic field minus the Laplace of the magnetic field is equal to epsilon 0 times the partial with respect to time of the curl of E, which from the third equation would be minus mu 0 dH dt plus sigma times minus mu 0 dH dt. Okay? From the first equation, the second equation, then we use the third equation here to replace the curl of E with the partial of H with respect to T. And from the second equation, we know that the magnetic field is solenoidal. So what I end up with is the Laplace of H is equal to epsilon 0 mu 0 times the second derivative of H with respect to T squared plus sigma mu 0 times the first derivative of H with respect to time. All right? And recognize C equal to the square root of the electric permeability and the magnetic permeability, such that C is the speed of light. So the speed of light is the square root of the electric permeability times the magnetic permeability, and then we can use that and replace these properties and end up with C squared, the second derivative of H, over t squared plus sigma divided by epsilon 0 times c squared dh dt. So now we've decoupled the equations. We have an equation for the magnetic field that's independent of the equation for the electric field. We can solve for it directly, and we'll learn techniques to solve equations like this. And this is called the damped wave equation. Damped wave equation for h. Remember, h is a function of x, y, z, and time. So it's a four-dimensional problem, and in space and time, and it's the space operator is a Laplace. The time operator is a second derivative. With respect to time, this is a wave-like behavior. This induces wave-like behavior, and this is a dissipative behavior. The first derivative with respect to time is dissipation, it's diffusion. So this is the damping term of the equation. Okay? If there were no electric resistivity, if there were no resistivity in the medium, then we just have the plain old wave equation. And so basically whatever we induce the field with, it's just going to propagate infinitely at the speed of light. So if resistivity is 0, that means sigma equals 0, then we have this equation, which implies undamped wave equation for h. So h propagates in time at the speed of light, and O propagates in space in response to the Laplace operator. Okay, so that's an equation that we'll learn how to solve. And similarly, Maxwell also decoupled the electric field from this equation by taking the curl of equation number 1. Curl of equation number 1 being, of equation number 3, I'm sorry, the curl of E should be equal then to minus mu 0 d dt of the curl of H so this, using the same identity, this will be the gradient of the divergency of E minus the Laplace of E is equal to minus mu 0 d dt of the fourth equation that says that this is epsilon 0 dE dt plus sigma E. Because the electric field is solenoidal, and we end up with minus, or plus Laplace of E is equal to mu 0 epsilon 0 second derivative of E with respect to t squared plus mu 0 sigma the first derivative of E with respect to time. And mass of E is equal to the square of the speed of sound, second derivative of E with respect to time squared, plus sigma over epsilon 0 times the square of the speed of sound, dE dt. And that would be the damped wave equation. Equation for the electric field. So now we have an equation that governs the electric field on a medium with permeability epsilon and mu, and with resistivity sigma that we can solve for, as long as we have boundary conditions and initial conditions. Right. All right, so this last section here on applications to electromagnetism is just for informational purposes. Later, we're going to, as I said, use that equation, try to solve it. But for now, you won't find examples like this in the homework or anything like that. Maybe the proof of that particular identity or such, and you should not expect to see anything like this on the exam as well. The solution of these will come later in the semester. All right, are there any questions? All right, great. So next week on Tuesday we'll stop here for field vector theory, and we'll start with curvilinear coordinate systems, and then we'll come back to vector theory because we are going to show all these vector operators and identities in other coordinate systems as well. So that's going to take us a week and a half, and that will be the material for exam number 1, and that will give you enough to also be able to solve those problems in assignment number 1. All right, so have a nice weekend, and I'll see you Tuesday.